Now we are starting with the first chemical property of group 15, that is reaction towards hydrogen. So we see that whenever anything reacts with hydrogen, it forms its respective hydrides, right. Likewise, the 15 group elements also react with hydrogen and form their respective hydrides. And if we talk about the valency, like what kind of oxidation state they share with the hydrogen, so they form trihydrides, that is in the formula NH, or you can simply write, like if I write the element as E, so it is EH3. The most of the hydrides they form this EH3. So we see that like nitrogen form NH3, which is commonly and popularly you can say called as ammonia. Phosphorus form PH3, which is called as phosphine. Arsenic form ASH3, called as arsine. Antimony forms antimony hydrides, called as stibine, and bismuth form bismuth hydride, called as bismuthine. I think it's right. Ammonia, phosphine, arsine, stibine and bismuthine. So these are the common hydrides which they form, that is in the formula of EH3. Now if we want that how we actually prepare them, so there are certain hydrides which can be prepared directly, like ammonia can be prepared directly by reacting N2 and H2 by popularly called as Haber's process, you know that. And what is that? In which we compress this gas N2 and H2 and atmospheric the pressure required is 200 to 300 atmospheric pressure, and even high temperature is required, approximately 400 to 500 Kelvin, and there is a catalyst iron and a promoter molybdenum oxide, and it forms ammonia. So this is what that here you can see that it directly forms, that is N2 and H2 under these given condition, high pressure, high temperature, and in presence of catalyst iron and a promoter molybdenum oxide, it is forming the ammonia. Otherwise we can also have the hydrides not obtained directly but indirectly, like by hydrolysis of their metal compounds. So we have their metal compounds, let us say I have magnesium nitride or I have calcium nitride, so I can just hydrolyze it, that is in presence of water I can just lyse it. So how it lies, we know that H and OH split this way. So what happened, we know that metals have great affinity for forming hydroxides, so it will form magnesium hydroxide and N and H will form ammonia. Likewise here calcium will form calcium hydroxide and N and H will combine to form ammonia. So we can form actually by hydrolysis of their metal compounds. Likewise we can also form by the reduction of their chlorides, but not for bismuth particularly. We cannot use this method for bismuth. Other than bismuth, like for nitrogen, phosphorus, arsenic and antimony, we can have their chlorides and we can just reduce them in the presence of powerful reducing agent, that is lithium aluminium hydride. So I suppose I have this NCl3, I am going to reduce it in presence of this reducing agent. So what do I have? I have NH3, I have LiCl and I have aluminium chloride, right. So by reduction of their chlorides in presence of LiLH4 we can have this kind of compounds. So these are the methods by which we can prepare hydride. So we can prepare it directly like I did for ammonia, we can prepare by hydrolysis of their metal compounds, or we can have by the reduction of their chlorides, but particularly not used for bismuth. So now if we talk about their characteristics, so we see that if we talk about their structure first, so these all hydrides are sp3 hybridized. They are all sp3 hybridized because they possess lone pair, therefore their geometry is not tetrahedral, it is distorted tetrahedral, that is pyramidal, right. So what is the structure? It is like that, in which you can see there is one N bonded to H, H and H, and there is a lone pair. Now because it has the bond pair repulsion also and lone pair bond pair repulsion also, therefore their angle is actually actual decrease from the tetrahedral one, and it is 107.8 dash. It is the actual angle, and why it is being it decreases due to increase like it has another kind of repulsion as it possesses the lone pair also. So there is bond pair repulsion also and lone pair and bond pair repulsion also. That is why we know that lone pair and bond pair repulsion is always higher. Like if we try to sum them up, we know that lone pair repulsion higher than lone pair bond pair, and which is higher than further bond pair and bond pair. So here there is only one lone pair, so there is no such repulsion, but we have this kind of repulsion. So that means lone pair will just try to it will repel bond pair because the repulsions are quite high, and the bond pair will start coming together, therefore the angle decreases to 107.8 dash, otherwise it is 109.15. So this is what is the angle. Now if we talk about the angle in NH3, PH3, arsenic hydride and this tibine and the bismuthine, we see that as you can see, the bond angle is gradually decreasing. The bond angle is gradually decreasing. Now what is the reason that bond angle is gradually decreasing? The reason is, see, nitrogen is small and suppose hydrogen is comparable, right. Phosphorus will be comparatively big and there will be a you can say repulsions between them still exist. Arsenic will be more bigger and but hydrogen will remain same, antimony will be more bigger, bismuth will be more bigger. So that means as we are moving down, the size is gradually increasing, the size is gradually increasing. But if we talk about the size of hydrogen, it remains as such, it is not getting changed. So here hydrogen size is comparable with the nitrogen. Here the hydrogen size is again comparable, phosphorus is bigger but still it is comparable. Arsenic is bigger and antimony becomes much more bigger and bismuth is much more bigger, but the size of hydrogen remain as such. So if we talk about the repulsions, so repulsion goes on becoming minimum and minimum because the size of an atom is increasing but the hydrogen size is remain the same. So there are not so much repulsions, magnitude of repulsion seen in this case as compared to NH3. So that is why the bond angle is decreasing, means they try to come closer to each other. Now if we talk about the characteristics of these hydrides, the first characteristic I have is basic strength. You know that what is the criteria to talk about the basic strength? It is the presence of lone pair. It is the presence of lone pair. So as you can see that they have lone pair, so that means they act as Lewis base. They act as Lewis base because they have electron, they can donate it to anybody, right. So if we talk about their basic strength along the group, we see that it is actually in order that this is more basic, this is more basic and it is in order like this. That means NH3 is more basic. Now reason being is nitrogen is very small in size, we know that. So that means being small, its electronegativity will be more and electron density will also be high because it is of small size. So obviously the same number of electron is concentrated in the small space. So that means electron density is comparatively high. So therefore its basic character is obviously high. But as we move down, we see that size is increasing and electronegativity is decreasing. Obviously electron density will also increase because the size gets increased, due to which the basic strength actually decrease. Because basic strength is one where the electron density is high. Obviously electron density will be higher in a smaller one or a bigger one, obviously in the smaller one. So we say that basic strength is more for NH3 and least for bismuthine. Second is thermal stability, which will be thermally stable, like where the bond will be more you can say more strong. So we see that it will be more, it will also again form the same order, that NH3 bond will be more strong and this will be least it won't be thermally stable. We can heat it and they will get separated, but it will be quite stable. The reason being, we know that small cation can stabilize small anion and bigger cation can stabilize bigger anion. As nitrogen and hydrogen both are of comparable sizes, so that means the bond formed between them is quite strong. But if we compare bismuth and hydrogen, hydrogen is smaller and bismuth is quite big. So do you think that a bond can be can be strong between a big atom and a small atom? No, not at all, because a small cation can stabilize the small one and the bigger cation can stabilize the bigger anion. There is always a symmetry we need in a bond and it does not exist in the bismuthine. Third is the reducing character. So let us not take reducing character first because its order is actually different, you will get confused. We will take another factor, let us take strength of MH bond. So we see that, as I have told you, thermal stability, obviously it corresponds to the strength also. Where the strength is weak, where the bond is weak, obviously it is weak in the bismuthine and it is strong in the NH3, because again the same reason, small cation can stabilize the small anion, means like cation stabilize the like anion. And if we compare of solubility, we see that NH3 is more soluble in water and bismuthine is least soluble. The reason being, it is smaller in size, it is capable of forming more hydrogen bonds, or you can say, we know that smaller is the atom, more it gets hydrated, more you get the hydration energy, and more is the hydration energy, obviously more is the solubility. So because being smaller in size, so that means it can form more hydrogen bonds, and as a result there will be more hydration energy, and we know that when there is more hydration energy, that means means it is more soluble in water. So this is over and this is over, you know now. Now coming on to reducing character and boiling point and melting point. You know that like in these two properties order is quite different. Like it is like if we talk about this. So what is the order in this case? It is more and nitrogen, ammonia is least, showing in like if we talk about these two properties. Now coming on to the reducing character. What is reducing character? Reducing character is the one in which the release of hydrogen is more easy. So where it will be more easy? Obviously it will be more easy where the bond is weak, and where the bond is weak, obviously it is weaker in the bismuthine, because the bismuth is quite big and hydrogen is quite small in size. So that is why reducing character increase in this order. So it is more reducing, it has more reducing character and it has the least one. Next is melting and boiling point. Again it follows the same order. Now the reason being, as you know that melting and boiling point actually depends upon the van der Waals force or a type of force or that exists between the molecules. So as we are going down, we know that the size is increasing and even the molecular mass of the compound is increasing. Like if we talk about the molecular mass of NH3 and bismuthine, obviously this is going to be higher because bismuth is quite big in size, and whenever there is increase in the molecular size, we know that van der Waals force actually increase, and when the van der Waals force increase, obviously the melting and boiling point increase. So this is what you can discuss the properties of the hydrides, and this is what is the reactivity towards the hydrogen, that is the respective hydrides formation.